Hello, my name is Sharon Smith, and I'm going to use this presentation session for a discussion on the engineering used in the Smithfield Street Bridge project. The Smithfield Street Bridge was constructed using structural engineering techniques, and these techniques were innovative enough to allow the structure to be named an American Society of Civil Engineers Historical Landmark. Two aspects of structural engineering to be discussed in this session are its design as well as the materials chosen for this bridge. Before the Smithfield Street Bridge was erected, there were two failures. The first failure was a bridge made up of wood. Wood is a flammable material with a low thermal expansion and was destroyed by a city fire. The second bridge failed because the yield strength was not enough to keep up with the growing and expanding population of the city of Pittsburgh. As horses and buggies got heavier and wagons got heavier and means of transportation evolved, the bridge began to shake, displaying a factor of safety, which is a warning sign some materials display when they are about to fail. So the Smithfield Street Bridge needed to be comprised of a design that was strong and lasting, as well as a material that wasn't easily yielded. The need of the design was met by the lenticular truss design. This design came from engineer Gustav Lindethal, and this truss design one of the first times it was introduced to America was through the Smithfield Street project. This lenticular truss design is made up of two sets of trusses that are shaped parabolically and as lenses, and it's comprised up of webbing, an upper and bottom cord, as well as panels and rods intertwined. The top cord, as well as some diagonal panels, are compressive members, while parallel rods and bottom cords are tensile members. The compressive and tensile aspects work together as the bridge carries a dynamic load from start to finish, transferring the stress from tensile to compressive member and so on. This also eliminates some of the stress concentration that can happen in a structure. Stress concentration happens at any change in geometry, a sharp corner, a sharp curve. It allows the stress to concentrate in one area, significantly decreasing the yield strength. So Gustav, the engineer, decided that the material to be used in the bridge would be open hearth steel, which was cheaper than wrought iron and displayed similar strength capabilities. The compressive members of the bridge were to be having minimum ultimate yield strength range of 80 to 90,000 pounds per square inch, while tensile members were to have a minimum of 70 to 80 pounds per square inch. So open hearth steel materials were chosen because due to its rapid cooling procedure, the tensile power was significantly strengthened. The steel would be heated on an open hearth, removed and placed in water rapidly, and that allowed the material to be extremely malleable without fracturing, so it could be shaped in the needed way without fracturing or yielding. It was also very accessible, which is a desirable characteristic to have in structural engineering. It was made right in Pittsburgh, where the project was being constructed. These are just a few of the structural engineering traits and aspects that were used in the construction of the Smithfield Street project. Thank you for listening.